Entangled realms, exploring the mysteries and applications of quantum entanglement. Join our journey now. Welcome back, Star Seeds. Before we get started, please don't forget to subscribe and also check out my description below for free astrology reading for 2023 and how to attract wealth with your DNA. Let's begin. Quantum entanglement is one of the most intriguing phenomena in the world of quantum physics. At its core, entanglement refers to the connection between particles that persists no matter how far apart they may be in space or time. The significance of this phenomenon lies in its potential to revolutionize the world of quantum technologies, from quantum computing to cryptography to teleportation. The discovery of quantum entanglement can be traced back to the early 20th century, when Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper on what they called spooky action at a distance. This paper was a critique of the emerging field of quantum mechanics, which they believed was incomplete. They proposed that particles could be entangled in such a way that the properties of one particle would be determined by the properties of the other, even if they were separated by vast distances. The significance of quantum entanglement for the development of quantum technologies cannot be overstated. In particular, entanglement is essential for the development of quantum computers, which promise to revolutionize computing by exponentially increasing computing power. Furthermore, quantum entanglement has the potential to revolutionize cryptography, with the development of uncrackable codes that rely on the properties of entangled particles. And finally, the potential for quantum teleportation, which relies on entanglement to transmit information instantaneously across vast distances, has captured the public imagination and is spurring research in this field. The most famous example of quantum entanglement is the EPR, Einstein-Podolsky-Rosen, paradox, where two particles are created together, then sent in opposite directions. If you measure one particle's property, such as its spin, the other particle's spin is instantly known, regardless of the distance between them. This has been verified experimentally many times and is considered one of the cornerstones of quantum mechanics. In nature, quantum entanglement can be observed in a variety of phenomena. For example, photosynthesis in plants appears to rely on quantum entanglement to transfer energy from one molecule to another efficiently. In addition, researchers have observed entanglement in the behavior of electrons in metals, and in the behavior of light particles, photons, in experiments. Overall, quantum entanglement is a fundamental aspect of the quantum world that defies our classical intuitions. Its implications have led to new fields of research and potential technologies, which may revolutionize the way we think about computation, communication, and cryptography. Quantum entanglement refers to a phenomenon where two or more particles become connected in such a way that the properties of one particle are intimately related to the properties of the other, regardless of the distance between them. When particles are entangled, measuring one particle's property instantaneously determines the corresponding property of the other particle, even if they are separated by great distances. In contrast to classical entanglement, which can be observed in everyday phenomena like magnets, where spinning electrons in one magnet align with those in a nearby magnet, quantum entanglement is more complex and involves multiple properties of particles, such as their spin or polarization. In the quantum world, entanglement is a fundamental property of matter that is a hallmark of the bizarre, counterintuitive nature of quantum mechanics. One of the most fascinating aspects of entanglement is non-locality, which refers to the fact that entangled particles can be separated by any distance, and yet, the properties of one particle will always instantaneously affect the properties of the other particle, regardless of the distance between them. This has been demonstrated experimentally many times and is a fundamental aspect of the quantum world. Bell's theorem is a crucial concept in understanding the behavior of entangled particles. It is based on the idea of local realism, which is the belief that physical properties exist independently of observation, and that information cannot be transmitted faster than the speed of light. Bell's theorem shows that in some cases, local realism is not valid, and this has been experimentally demonstrated through the violation of Bell's inequality. The violation of Bell's inequality indicates that entangled particles are not separate entities with independent properties, but rather they are part of a single system with a set of correlated properties. One demonstration of the violation of Bell's inequality involves two entangled particles sent to separate detectors. The detectors measure the properties of the particles, such as their spin or polarization, and the results are compared. If local realism were valid, then the results would be independent of each other, meaning that there would be no correlation between the measurements. However, experiments have shown that this is not the case, and the measurements are correlated, which violates Bell's inequality. Quantum entanglement has a number of potential applications, some of which are already being developed and tested. 3 of the most significant applications of quantum entanglement are in quantum computing, quantum cryptography, and quantum teleportation. 8. Quantum computing. Quantum computing is an emerging technology that has the potential to revolutionize the way computers process information. Unlike classical computers that use bits, which can be either 0 or 1, to process information, quantum computers use quantum bits, or qubits, which can be both 0 and 1 at the same time. Quantum entanglement is used in quantum computing to enable multiple qubits to be linked together, allowing for more complex calculations to be performed. By entangling qubits, quantum computers can solve certain problems exponentially faster than classical computers. The advantages of quantum computing over classical computing include faster computation, increased processing power, and the ability to solve certain problems that are beyond the capability of classical computers. B. Quantum cryptography. Quantum cryptography is a method of secure communication that uses the principles of quantum mechanics to protect information from interception or eavesdropping. Quantum entanglement is used to distribute cryptographic keys that are used to encrypt and decrypt messages. In quantum cryptography, entangled particles are used to generate a shared secret key. The key is then used to encrypt the message, and the receiver uses their half of the entangled particle pair to decrypt the message. Because of the properties of entangled particles, any attempt to intercept or eavesdrop on the communication will be immediately detected. The advantages of quantum cryptography over classical cryptography include increased security, as it is impossible to intercept or eavesdrop on the communication without being detected. C. Quantum teleportation. Quantum teleportation is a process in which the quantum state of one particle is transmitted to another particle, regardless of the distance between them. Quantum entanglement is used in this process to transfer the quantum state from one particle to another. In quantum teleportation, 2 entangled particles are created, and one of them is sent to the receiver. The sender then performs a measurement on their particle, which changes the quantum state of both particles. The result of the measurement is then sent to the receiver, who can use it to change the quantum state of their particle to match the original quantum state. The implications of quantum teleportation for communication and transportation are significant, as it could potentially allow for the instantaneous transmission of information and matter over long distances. In summary, the applications of quantum entanglement are diverse and significant, with potential uses in quantum computing, quantum cryptography, and quantum teleportation. These technologies have the potential to revolutionize the way we process information, communicate, and transport matter, and will likely be a key area of research and development in the coming years. While quantum entanglement has many potential applications, there are also a number of challenges and limitations associated with this phenomenon. 3 of the most significant challenges and limitations are the problem of decoherence, the challenge of scaling up quantum systems, and the potential security risks of quantum technologies. A. The problem of decoherence. One of the main challenges associated with quantum entanglement is the problem of decoherence. Decoherence occurs when a quantum system interacts with its environment, causing the entangled particles to lose their entanglement and become separate entities once again. This makes it difficult to maintain and manipulate entangled states over a long period of time, which is essential for many quantum applications. B. The challenge of scaling up quantum systems. Another challenge associated with quantum entanglement is the difficulty of scaling up quantum systems. While it is possible to entangle 2 particles, scaling this up to larger systems is much more challenging. This is due to the complexity of entangling multiple particles and the fact that the system is more prone to decoherence as the number of particles increases. C. The potential security risks of quantum technologies. While quantum technologies have the potential to revolutionize the way we process information and communicate, they also pose new security risks. For example, quantum computers could potentially break many of the encryption schemes currently in use, allowing sensitive information to be accessed by unauthorized individuals. Similarly, quantum cryptography could be vulnerable to certain types of attacks, such as those that exploit weaknesses in the hardware or software used to implement the technology. While quantum entanglement has many potential applications, there are also a number of challenges and limitations associated with this phenomenon. These include the problem of decoherence, the challenge of scaling up quantum systems, and the potential security risks of quantum technologies. It is important to address these challenges and limitations in order to fully realize the potential of quantum entanglement and the technologies that rely on it. Quantum entanglement is a fascinating phenomenon that has captured the attention of scientists and the general public alike. It allows for particles to become inextricably linked, resulting in a number of potential applications, including quantum computing, cryptography, and teleportation. While there are still many challenges and limitations associated with quantum entanglement, it has the potential to revolutionize the way we process information and communicate. Continued research and development in this field will be essential in unlocking the full potential of quantum entanglement and the technologies that rely on it. Thank you for watching Starseed TV. Please don't forget to like and subscribe. Thank you with love and gratitude. See you in my next video.